Hi, the question states that a thin spherical insulating cell of radius r carries a uniformly distributed charge such that the potential at its surface is V naught. Okay. Now, a hole was with a small area alpha 4 pi r square, where alpha is very small. That means this area is very small as compared to the surface area of the sphere, is made on the cell without affecting the rest of the cell. Which of the following statements is correct? Option A: the magnitude of electric field at a point located on a line passing through the hole and cell center on a distance 2r from the center of a spherical cell will be reduced by alpha times V naught by 2r. Second option, we have to find out the magnitude of electric field at the center and whether it is reduced by alpha V naught by r or not. Okay. Option C, the ratio of potential at the center of the cell to that of the point at r by 2 from center towards the hole will be 1 minus alpha by 1 minus 2 alpha. And option D, the potential at the center of the cell is reduced by 2 alpha V naught. Okay, fine. Now, given the condition is, suppose this is a spherical cell where the potential is V naught, which is given in the question. Suppose we have to give a charge of Q to have a potential of V naught. So let Q is the charge on the capacitor, on the spherical cell. Now we can say that this potential can be written as KQ by R. So it is the potential because of uniformly distributed charge on a spherical cell. So it is KQ by R. So this can be written as V naught. Now suppose this white patch is the small area that is equal to alpha times 4 pi r square, and alpha is very small, so this small area is very small, and this small area is removed now. So now this is removed area, and this area is alpha times 4 pi r square. So let the charge associated with this area which we have removed is delta Q. So this it will be now we have Q charge, so which we have assumed we have Q charge on the area of 4 pi r square. So definitely if you want to have a charge associated with the area as alpha 4 pi r square, then we can write delta Q as alpha times Q. Okay. Now this small area is very small that this patch can be treated as a point mass, and there is a charge delta Q which is associated with this point mass. Okay, so now for this scenario, what we can assume that we have a charge Q, that is positive charge on this entire spherical cell, which is uniformly distributed, and there is a negative charge of delta Q which we have kept from outside. Okay, so now what will happen that in this region of in this region of alpha pi r square 4 pi r square, the net charge will be 0 because Q is the positive charge on the surface and delta Q is the negative charge which we have kept in this small area. Okay, so we can assume like that we have there is a superposition of positive and negative charge in this area. So here there is no charge. Okay, so it is the other way of saying the same thing which is given in the question. Fine. Now option A, so where we have to find out the magnitude of electric field at a point P, which is at a distance 2r from the center and r from this patch and passing through the center. Now the electric field at point P can be written as the electric field because of this entire Q charge, and at the same time the electric field because of this small patch, and this I'm treating as a point charge because the area is very small. So we know that for this spherical cell the distance is 2r, so we can write ET minus ER I'm writing because this I'm considering as negative. Okay, negative charge, that is delta Q. So KQ by 4r square. Why? Because this is 2r from the center. Now this is KQ, where charge is point charge is having a charge of alpha Q by r square. So this is the final. Now initial, what was it when we have when there is no removal of the charge? Then definitely it will be KQ by 2r square, that is KQ by 4r square. So definitely the change in electric field that can be written as final minus initial. So definitely this will get cancelled out, and we will have minus K alpha Q by r square. So that is the change in electric field at that point. So this we can also write as minus V naught alpha by r, where minus denotes that this is a reduction in the electric field at that particular point. So option A is incorrect. Now option B. So option B, where we have to find out the ratio or the reduction or the increasement of the electric field at the center. So initially, it was a full spherical cell, and there was a charge Q, which is having a potential of V naught. So initially there was no electric field at the center because it was uniformly charged. Now final, there is electric field, and that is because of the point charge which we have kept. So that is K delta Q by R square, because the center is at a distance of R from that point charge. So this is the point charge, and center is at a distance of R from the point charge. So this is the final, because we have introduced a delta Q from external source, and that delta Q is negative. So that is, we can write K alpha Q by R square. So this is the magnitude of electric field. So definitely we can write V naught alpha by R. So B is also incorrect. Why? Because the electric field initially it was 0, and finally it is V naught alpha by R. Okay, which is not matching with the option which is given in here in this case. Now option C. So we have to find out the potential at point P. So the and we have to find its ratio with respect to potential at C, center. So potential at point P can be written as the potential because of the sphere that is KQ by R, and because of this point charge, that is K delta Q by this distance, which is R by 2. Okay. Now this, if you just solve it, then you will get KQ by R 1 minus 2 alpha. Now, if you want to write the potential at C, that is the center of the sphere. So because of a sphere, it is KQ by R. Same, because for any point, if you take any point inside the sphere, because of the charge on the sphere, it is KQ by R only. And because of this point charge, we can write at minus K delta Q by R. So if you take the ratio, then you will have 1 minus alpha by 1 minus 2 alpha. So option C is correct. Now let's go to option D, where we have to find out the change in potential at center. So initially there was no delta Q, so KQ by R was the initial. Now final, there is a delta Q also, so it is KQ by R minus K delta Q by R. So the change in potential will be minus K delta Q by R, that is alpha times V naught. So there is a reduction, there is alpha times V naught. So this option D is also incorrect. Okay, so now I hope that this is clear to you. Thank you.